I'd like to thank Heather for inviting me to speak here. I'm not a statistician by training, I'm a theoretical physicist by training, but over the last couple of years I've been working quite intensively at the interface between quantitative modeling and medicine, and specifically in survival analysis. So what I'm talking about today is sparsity in the sense of us having only a modest number of samples relative to the dimensionality of the problem that we are studying. And my talk will be roughly in 3 parts. I'm first going to introduce you to the concept of overfitting in survival analysis. I'm going to show you some of the phenomena that are caused by overfitting. Then I will try to explain how our intuition, which tends to be based always on low-dimensional structures, sometimes misleads us when we think about very high-dimensional covariates. And then the question is, can we build a quantitative theory to understand exactly what is going on in overfitting, with the aim to then be able to correct our regression results for the effects of overfitting? And that is a section that I will not do in full detail. I'm not interested in talking about the technicalities, but I will focus on the principles or the ideas that went into the model. And I end with some applications to Cox regression, regularized Cox regression, and other extensions to more generalized linear models. Okay. So, as I said, I'm interested in medicine. Survival analysis, of course, is also applied in other areas. But in medicine, we are increasingly in a position where we have very large amounts of data, and they are just rusting away in databases. And the NHS is really very upset about this, because what we really would like to do, we find ourselves unable to do. We would like to use all these high-dimensional data, genomic data, images, to develop a personalized medicine. But to do personalized medicine, we need complicated models. We need models with many parameters that look at all these high-dimensional data, that can deal with all the tricky aspects of medical data, such as disease heterogeneity, such as confounding factors. And of course, by definition, when we have very complex models with many parameters and modest numbers of samples, we're in trouble with overfitting. So this is a very basic obstacle in the use of all the expensive data that we have nowadays in post-genome medicine. So what does overfitting generate when we are looking at survival analysis specifically? Well, the obvious thing, first of all, what we see when overfitting happens is that we are doing extremely well in predicting outcomes with our models on data that were used to train the models, but we are getting very poor prediction results when we then apply the model with the parameters that we found to unseen data. And a very simple way of seeing this is, these are real data, these are breast cancer data, is to do the following type of numerical experiment. Here we had about 36 covariates, so you start a regression with all your covariates. You divide your data set randomly in 2 halves, use 1 half for training, the other half for validation, and then you simply try to predict whether or not an event occurred prior to a given time that is like the median or the average. And if you do that, you find that in the overfitting regime, if you count the fraction of correct predictions your model will give, you use your Cox model then in predictive mode with the Breslov estimator, then you will find that you do very well on the training set. You get a nice fraction correctly predicted, but you do very poorly on the data that weren't used. Then what you can do, you can identify via some protocol the least relevant covariate, and you do the same thing again, which means you will be moving to the left step by step. And if you repeat this process until there is no more covariates left, you will see a typical set of curves like this. And to any machine learning person, this is the standard fingerprint of overfitting. Yeah? So there is a point up to which things work really well, but from this point onwards, you will increase your performance on the training data, but you're not just not improving on the validation data, your performance actually goes down. So this is the standard phenomenon of overfitting. Okay, people are aware of this, of course, and what happens is that many use rules of thumb to avoid crossing this point. Yeah, and one obvious or very popular rule of thumb is you should have a number of covariates that doesn't exceed the number of events divided by 10. But this is a primitive thing. And if you look at the paper on which this rule of thumb is based, these are very small samples with relatively few numbers of covariates. It's an old paper, and it seems to be not only too optimistic, but also you don't really expect that whatever this point is, that it should not depend on covariate correlations. It's just not what you expect. And you should also expect that it should depend on the strength of the true signal somehow. That cannot be really a universal number. But this is intuition. But this is what you see. Now, what else can you do to see what goes on in overfitting? This is another simple thing to do. There's no serious regression being done. The thing you do is you generate data, synthetic data from a Cox model, say, and then you compute the univariate estimator for the regression coefficients, and let's say the Pearson or the rank correlation with outcome, and you just plot all your covariates in the diagram like this. Then, dependent on how many truly associated covariates you put into your synthetic data, and here I've chosen to have 30 true associations, and the rest of the associations are spurious. So in the data generation, there wasn't any non-zero beta. And then you can just plot what you get, and then you see the following. If in this plot I've shown in green the covariates that are truly associated, and in purple dots the ones that really should give me beta equals 0, but they don't. And of course, the more you increase the number of spurious covariates in your data, you see these purple dots appearing, and these are false positive associations. And you see it's really impossible to see the difference between the purple and the greens. Right? There's nothing that distinguishes them in these diagrams. So this is another way of looking at it. One aspect, at least, of overfitting, you will generate a lot of false positive associations. Now, something that starts to be a bit more interesting and revealing is this experiment. Let's look at the top left diagram. So what I did here is I'm running a multivariate regression, and for each covariate I plot horizontally the true value of the coefficient beta, which I know because I've generated synthetic data, and vertically I plot whatever comes out of my multivariate Cox regression. Now, in an ideal world, with numbers of covariates that are relatively small, all these points should be on the diagonal because the inferred value should be identical to the true one. But of course, if you increase the dimensionality of the problem, if you increase the number of covariates while keeping the number of samples fixed, it's going to get, the method is going to get into trouble because of overfitting. But the way it gets into trouble is very peculiar. So what I would have expected initially, and I was wrong, is that if you increase this ratio of the number of covariates over the number of samples, that you just get a bigger cloud. Well, you do get a bigger cloud, but the dominant effect is a tilt. Yeah? And that points at a reproducible bias. Yeah? The dominant effect is not noise, it is a really predictable bias, which always tends to exaggerate the values of associations. Because if you look here, then you see that if a true covariate is, a true parameter is a half, it's going to be reported at something much bigger. Same for negative values, they're going to be reported as much more negative than they really are. But when something is predictable, we're in business. We can start to model it, and we can start to try to predict that angle. And this is going to be the aim of the theory, that is to predict this slope. Because if we know the slope, we can correct for it. We can just rotate these points back to the diagonal. And then we have an overfitting correction. So similarly, if you look at the Bayes hazard rate that you infer, and this is via Breslov's estimator, there is a very reproducible bias as a result of overfitting. It is not noise. There is some noise, of course, but here I show the integrated inferred Bayes hazard rate for data where the true Bayes hazard rate was constant. So the integrated one should have been this dashed line. Instead, if you increase that ratio of covariates over samples, you get this type of phenomenon. So that means that the slope of this, which is the inferred Bayes hazard rate, seems not to be constant, but to increase for larger times. And this happens for any shape of the true Bayes hazard rate, and this is extremely reproducible. If you do the same thing again with new synthetic data, you get curves which are more or less on top of this, apart from the little noisy wiggles that you see. So again, there's something very reproducible about how overfitting messes things up. It is not tipping noise over your inference. There is something that is reproducible. Okay, so let's try to think about our intuition. There are all kinds of funny things happening when you have high-dimensional covariates. And remember, our intuition is always based on this low-dimensional maximum likelihood MAP regime, where the number of samples increases, but we keep the dimensionality of the parameter space fixed. In the high-dimensional regime, which we're interested in, we send both n and p to infinity, but at a fixed ratio. Now, some things we already know, and that is that standard p-values in Cox regression, they are blind to overfitting. They're not meant to report on this. Yeah? They just report on the noise. But some other things are less obvious. First of all, that hyperparameters of priors, in fact, should be p-dependent, and I will show you why in a few slides. And this is not what people tend to do. Moreover, if you have sufficiently large numbers of samples, in contrast to what intuitively you think, it will be possible to do regression even when the dimensionality is larger than n. And I'll come back to that too. So let's introduce some notation. Usual stuff. We have data which consists of pairs of covariate vector set, corresponding event times. I'm here just looking at one risk, but all this can be generalized to multiple risks. Cox model, standard form. Maximum likelihood inference, we maximize the probability of the data given the parameters. In this case, the parameters are the vector beta in the Cox model and the base hazard rate. And MAP inference, we would in addition have a prior in the parameters, and most people do not introduce a prior for lambda, but only for beta, because otherwise things get really very messy. So this is the standard protocol. I'm looking at this type of inference processes. Now, let's look at this comment I made about scaling of hyperparameters, because this is not immediately obvious, at least it wasn't to me. So I repeat here what we do in MAP regression. So we have the probability of the parameters given the data expressed in probability of the data given the parameters and the prior. We take a logarithm and it decomposes like this. And P of beta would be the prior that we choose. And there are many priors. People have different choices, but the two dominant ones are probably the L1, what gives rise to L1 regularization and L2. And in all these choices, we have a hyperparameter which basically sets the scale for the values of the coefficients here and here. Now, my claim is that you can show that this width parameter should not be a constant, but should be 1 over square root p, where p is the number of covariates. So the prior should actually have a hyperparameter that depends on the dimensionality. And there are two ways to see this. One, it follows from the general theory that I will show you later, but there's also an intuitive reason that is more obvious. And that is, just ask yourself if p is really large, and if this width were just an order 1 number, what would happen? Well, in the Cox model, let's say everything that depends on the characteristics of a patient is channeled via this inner product. Yeah? Sum of coefficients times covariates. But in the simplest case already, let's say the covariates are chosen independently and they are order 1, and the betas are order 1, then this is a number that would be distributed around 0, but of width square root p. Yeah? It's a sum over p random numbers, all of them are order 1, positive, negative. But that means that all your event times would be either 0 or infinity. Yeah? Because there would be diverging negative values for some patients and diverging positive values. But if p becomes very large, you would not observe finite event times. So the very fact that we know from our data that we observe finite event times tells us that this is how the beta should scale. Yeah? So this prior has to have a sigma here that is 1 over square root p. And for instance, if you choose an L2, putting 1 over square root p here means a p comes outside. Yeah? So these are things that you normally don't get if you look at low dimensional situations. Now the other claim, this is also something that you normally don't run into, but if p becomes really large, it is an interesting observation. Let's say we have regression with a large value of p and a large value of n. and we ask ourselves, how likely is it to get false positive associations reported, let's say in a univariate analysis. Then we know that the value of n and p will have an impact on this number, but it will go in opposite ways. Increasing n will make it less likely to see a false positive association. Increasing p will make it more likely, because I just have more chances of running into one. And the crucial question is, how does this competition play out? And it turns out, if you work out your equations, that the n is going to win, ultimately. Because what you can compute is a number that tells you the following. This critical value, nc, is the point where the probability of finding one or more spurious univariate associations of a given strength that you put as a parameter is less than q. And if you plot the values of these ncs, then these are basically telling you at this value of n, it becomes unlikely to see an association of this strength purely by chance, of all my p covariates that I study. And of course, the smaller the association, the harder it is to avoid the spurious associations. And here I've drawn the line n is equal to p, and you see you can always go over into this region, and in this region, n is smaller than p, and still, for each of these lines, I will arrive at a point where I can do regression, in principle. Doesn't mean we have the method, but it means that it is in principle possible, because the spurious associations will vanish. And you can see that also if you do just experiments with synthetic data, which is what I've done here. At some point, if you increase n and p, and here's where n and p are both equal to 800, these outliers in the purple clouds become extremely unlikely. Yeah? And at some point, I will be able to do regression, not for all values of the correlations, but those that are sufficiently strong will indeed survive and will indeed be distinguishable from the spurious ones. Okay, so all these things relate to the difference between having a low-dimensional covariate vector and having high-dimensional covariate vectors. Now let's work towards a theory. We would like to understand quantitatively, and not just on the basis of anecdotal evidence like I showed now. You would like to understand quantitatively what happens, so that we can actually do corrections. And to do this, we first need to get intuition for what is happening when you do overfitting. So let's go back to maximum likelihood regression. Now, maximum likelihood regression is based on maximizing the probability of the data given the parameters. And you can show very quickly that this is equivalent mathematically to minimizing a Kullback-Leibler distance. And it is the Kullback-Leibler distance between p hat, which is the empirical distribution of the data, just the histogram of the joint values of covariates and event times, and the model that we assume is responsible for the data. If you choose the Cox model, then this theta would be the base hazard rate and the association parameters. So minimizing this immediately brings you back to the maximum likelihood definition. And this is useful because it tells you why maximum likelihood works and where it will work. Because what maximum likelihood does is it pushes this parameterized distribution by changing the parameters of the model as close as possible towards the empirical distribution. And that makes sense, right? But it only makes sense if we are away from the overfitting regime. And the reason it makes sense there is that if we take sufficiently many samples, the empirical distribution will ultimately converge towards the true distribution from which the data were drawn. And let's say the data were drawn from a distribution with parameters theta star that we seek to estimate. And since the empirical distribution becomes this, if I minimize the distance between, p, between my p and this distribution, then, because Kullback-Leibler distance has a unique minimum, it will reproduce for me the true parameters. But if p is of order n, this empirical distribution in no sense at all looks like the true distribution, because you just have a few delta peaks here and there scattered in a very high dimensional space. So what you're doing with maximum likelihood is going to be wrong. You're going to find a parameterized distribution by manipulating your parameters such that it is as close as possible to this funny thing, which does not resemble the true data distribution. And this is the root of the problem. Okay, So how can we move forward and build a theory? And there's 3 steps, and I'm only going to show the ideas, and then you do lots of integrals and things, which is not interesting, but I will only show you results. But the ideas are important. So it is all building on this interpretation of maximum likelihood, and that can be generalized later to MAP, in terms of minimizing a Kullback-Leibler distance. So if we indeed minimize a Kullback-Leibler distance, which means we are pushing theta such that the parameterized distribution becomes as close as possible to the empirical one generated from a distribution with parameters theta star that we don't know, then what you can ask yourself, what would be the optimal stopping point? Already we know from the previous page that we shouldn't push all the way to p hat. Well, the optimal point would be if our algorithm stopped exactly when it achieved theta star. Now, and this distance would then not be 0. Yeah? You would find the distance between the empirical data distribution and my model to be the distance between the empirical data distribution and the model with the true parameters, but that would not be 0. This distance would reflect the mismatch between the true distribution and this funny, sparse realization of samples from this true distribution. So, but this suggests something. It suggests that what we should really be looking at is the difference between the value of the minimum that the algorithm finds and what I would want this distance to be in an ideal world. And then you have a number that tells you interesting things, because if it's positive, we know that we should have minimized further. We are underfitting. If it's negative, we have gone too far. We're overfitting. And what we then want to know is maybe not the value for this for each and every data set, but we're interested in the typical value, because I'm not interested in peculiarities of one data set. I'm interested in generic properties. So we would like to know the average of this over all possible realizations of the data set, generated from the same parameters and the same model. And then you plug everything in. Yeah, we have a definition of E in terms of Kullback-Leibler distances. You subtract, you manipulate, and then you find this. Yeah? You find that this object is the average of all data sets of the minimum over parameters of something like this. Yeah? Sort of like a cross-entropy type term, which involves the true parameters, which we don't know, and the parameters theta that we're minimizing over. So this is step 1. We have a quantity that we want to focus on. Step 2. What is the pain here? The pain is this horrible minimization, because averaging over a minimum is painful. But there's a way of getting rid of it, and that is using Laplace's identity. You can trade in minimization for performing an integral. Yeah? If we perform this type of integral, we have a parameter gamma, we send gamma to infinity. After differentiation, then we find the maximum of this function, provided all the integrals exist. We can therefore use this in reverse and write this in terms of an object in which we no longer have to do a minimization. But instead, we pay the price of having to do an integral and having to differentiate. So that's step 2. And you can actually interpret even what you get when you don't set gamma to infinity as a stochastic minimization, where this gamma parameter tells you about the noise. Now, last step. This is still painful. We have to do the average of the logarithm of something over the data. And remember, the data sit in here, the z's and the t's. And that's where the replica method comes in. The replica method is a method from theoretical physics that has about 50 years of tradition, but it has also been used in biology, immunology, in computer science, in economics. And it is basically a clever trick to turn averages that are not analytically feasible into averages that are analytically feasible. And this is what we wanted to do. I've just copied over the previous thing. We have the average of the log, and the pain comes from the log. And it is based on this cute identity. The average of a log can be written in terms of a limit of the log of averages of powers of this number. And the trick is that this would still be painful if n was not an integer. So what you do is you evaluate this for integer n, and then do analytical continuation to 0 at the end. And if you ask yourself, what is the consequence of this? Well, you have to ask, is it easier to perform averages over this object of powers of it than the logarithm? Yes, because if I have powers of this object, I just get multiple integrals. But all of a sudden, the average of the data becomes trivial. And you can work it out. And what you get, so this is what we get if we just substitute the identity, but now an integral to the power n can be written as an n-fold integration where we have replicated all these parameters theta, and we have an object in which the average over data sets could be done. So now we have something that is in principle completely well defined. The only thing that appears here is the actual model that we choose to work with. For instance, here you would substitute for your P the Cox model. Yeah. So this is the basis, and this method can be extended to include MAP, arbitrary generalized linear models. But it is technically still a bit involved to do all these limits and averages, but it is feasible now. So let me show you applications so that in between the previous page and this page would be a lot of work, but what you end up with is this. You find that ultimately you can take all your limits, you can look at large systems, and you get explicit formula for this quantity E. And the only place where the properties of the true parameters that we don't know still reside are in S, which is the absolute value of the true association parameters, and lambda star, the true base hazard rate. But you get explicit equations for a couple of quantities. One of them is the inferred base hazard rate and 3 scalar objects. And they involve Gaussian integrals, that's what the capital D stands for, and the Lambert function. So these things are numerically maybe not immediately trivial, but they are exact. No tricks, nothing. The only problem that we still have, oh wait, before I go there, is the nice thing also is that the quantities we are after, which is the slope of this data cloud and the width of the cloud, they actually follow from these parameters that I showed you on the previous page. The theory predicts those things. So the only thing that is non-trivial in the end is the equation for the base hazard rate. We have an explicit equation, but it is highly, highly non-trivial. You can study asymptotic properties, and you find for large times that there is a power law relationship between the inferred base hazard rate and the true base hazard rate. This we didn't know, but you can just check it out by plotting them, and then you see that this is more or less a line. Not fully, because you see there are also correction terms and so on. And you have explicit expressions for all these things. So because this equation is very, very hard to solve analytically, we've done a variational approximation where we use the fact that in leading order for large times, this is a power law relationship, and then we get some corrections, so we put that in. And this constant k takes care of some of the corrections. And then you find that your base hazard rate, the true base hazard rate, actually drops out of the equations, which is really nice. And you can show in the simulations that is actually correct. And what we then in the end have, a theory that predicts for us the width of the data clouds, it predicts for us the slope. If we increase the ratio between the number of covariates and the number of samples, at some point we get to see differences because of this variational approximation. So that's not a surprise, but one can improve upon this because we still have the exact equation for the base hazard rate. And so this was for the standard Cox model. Then for the regularized Cox model, you get some extra interesting things. So first of all, unlike the true Cox model, you can show in the true Cox model that covariate correlations drop out of the problem. You can transform them away. As soon as you introduce priors, and we chose the L2 prior because we don't want to mess up this nice property that we have data clouds that are linear, then of course you will get betas that can no longer, no, it's not immediately obvious, but let me just tell you what happens. You can no longer transform away the covariate correlations. They stay in your theory. And in particular, you find that you get, again, closed exact equations, but in there you find the spectrum of the covariance correlation matrix. But this is something that we know. Yeah? We have the data, after all. You get some extra order parameters in the theory. You no longer get a phase transition when the ratio P over N goes to 1, because you have a regularizer in the game. And everything is perfectly well defined. And what is extra that we didn't have before is that you also get, because you get an equation that couples the slope of the data cloud to all the other parameters, rather than computing the slope in terms of the parameters, you can also say, I play the game differently. I demand that the slope is 1 and ask myself which regularizer parameter would give me this. And you get exact equations for that. And the theory works well. These are plots for the width of the data cloud, simulations versus the theory. In the angles, you get a lot more noise, and if we do it for larger sets, then it takes longer, but you get better agreement, but still, qualitatively, you see what, what you are supposed to see. And this is for covariate correlations that are defined in a pairwise manner. And so in the end, what you now have, yeah, I'm nearly finished, is a protocol for overfitting corrections. And it would go like this. So you would estimate, first of all, your correlation matrix for the covariates. You find the eigenvalue spectrum. You do Cox regression with a regularizer parameter eta. This gives you a beta hat and a lambda hat. Then you can calculate a quantity that is used later to replace the amplitude of the true associations, which we don't know. You get an extra equation for that. You can calculate your slope, your noise amplitude. And then, because of the way the theory is set up, we can correct the inferred associations, and we can correct the inferred base hazard rate, the integrated one, for the effects of overfitting. And if you do this, you see all these clouds of points rotate nicely back to the diagonal. And this extra noise can then be used to correct your p-values by adding in the effect of overfitting. Okay, other extensions include basically all generalized linear models like logistic regression, ordinal class regression, and so on. So to summarize, overfitting in Cox regression leads you to a very important bias in your regression parameters, a bias in the base hazard rate, and extra noise that is not visible in your p-values. But you can develop an analytical approach based on the replica method that allows you to compute those things. And that, in turn, once you have quantitative tools to predict the bias, you can correct for the bias. And for the L2 regularized Cox regression, you can even get equations that tell you what the optimal regularizer should be. And you find papers on my website. Thank you for your attention.
You also studied the relationship between this overfitting, this study here, and model specification. How it works in the presence of model misspecification.
Yeah, so the question is, have you also studied the effect of model misspecification on overfitting? The answer is no, because we've been very, very busy pulling this off so far. But it is obviously one of the interesting next steps, yeah, because this allows you to carry it out, right? And you can do this in many different ways. What we did look at also is what happens if you have L1 priors. And then the problem is that you get a data cloud that is no longer linear, but it has a segment in it where the betas are mapped to 0, as you expect, yeah? And your integrals become much harder. But in principle, you can still develop the theory. But model misspecification, very interesting, and that's obviously a thing to do.
Yeah, especially because you have worked with Kohlberg-Libler criterion, and you know about the paper, White 1982? Is for this White paper by White 1982.
Yeah.
Yeah, that's it's based. They show that the maximum the misspecified estimator converge to the minimizes the Kohlberg-Libler information.
Yeah. So you're always minimizing a Kohlberg-Libler distance, but you're then minimizing a distance between a parameterized model and another parameterized model from a different parameterization family.
Right.
Yeah. So you can do these things.
Yeah. Thank you.
Yeah. The theory in that presentation was going way beyond me, but yet it seemed to me that you were doing a nice job of linking advanced theory to intuitions about data analysis. And I want to see whether I'm on the right track in my understanding of this. The fact that if you're just estimating variance in a simple regression analysis, the maximum likelihood estimate of the residual variance is biased. Is that, and that, if n minus p, if n is much larger than p, then that bias goes away. Yep. Is that a special case of the kind of thing that you're talking about here?
Yeah, because in linear models, you see exactly the same, because linear models are just a special case of generalized linear models, in the sense that you don't generalize anything. It's linear from the start. So yes, that is a special case. But the claim here is that for arbitrary, non-linear, generalized linear models, exactly the same happens. Yeah? You get exactly the same bias, and the bias helpfully takes the form of just multiplying by a single constant the values of all the association parameters. And that is not obvious. That it should have been like that in arbitrary, generalized, nonlinear generalized models is not at all obvious. But it makes this feasible. And you lose it if you go to L1, and things get harder as a result. So the answer is yes, this is a generalization of that, and it turns out to be generically true. And the whole theory you can set up and just leave your model somewhere. The only thing you need to use is that what is ultimately dependent on the covariates is dependent on the covariates via inner products. But it can be more than one inner product, as in latent class models. So that's why it can be generalized to logistic regression, discrete ordinal class outcome models, to, you name it, neural networks even, anything that has as its core these inner products. You always get that.
Thank you.
Well, thank you for a very nice talk. You motivated your talk by emphasizing the effect of overfitting on prediction error. And so I'm wondering, after you do your adjustment, what are the implications relative to the use of that model for prediction?
Yes, so one thing, and I didn't show that, and I should have included this picture. You can show that if you compute with your theory these angles, you can map your data clouds back to the diagonal, and they do end up on the diagonal. But what you're guessing, what you're suggesting, and you're absolutely right, that's the next thing, we now need to build that into our analytical pipelines and make sure that in all these multivariate regression, that correction is being done. And then it would be interesting to see what this picture becomes, the one that I showed you at the very beginning, the one where you get a separation between training and validation sets performance. Here, this one. So this is really the next thing, and this is what I hope to get soon. Because what I would expect is, on the basis of what we've seen, we can at least go all the way up to P is a half n, without serious problems. Now, if P is a half n, and this is 0.1, you can go up to here, because it was 36, 18. So I would expect now these two curves to start deviating roughly here, which means that we stay at a much higher level with a validation error. But that, I need to show that that happens. This is what I expect and hope, but you're right, this is the next thing. Yeah.
Okay, so I think for the interest of time, we have to move on. Let's thank Anthony again. So our next speaker is Peter McCullagh, who is going to talk about sparsity.
So I'm going to be talking about a simpler setting than the previous one, nothing complicated, nothing nonlinear. It's the very simplest setting where we just have multiple sites. I will use the term sites. And at each site, there is a signal, which I will denote by X, and an observation, which I will denote by Y. And the observation is just the sum of the signal and a standard Gaussian random variable. So it couldn't be much simpler than that, and in some respects this is artificially simple, but it turns out that it captures, it's sufficiently complicated to capture the main features of certain types of application, although not regression, unfortunately, because it's for various reasons, it's more complicated. The observations are not independent, essentially. Okay, so that's the setting. It was considered initially by Johnstone and Silverman in a paper in 2004. And they considered the case where these signals had a distribution that was sparse, but they were all independent at different sites and identically distributed. So essentially, all of the sites are exchangeable in this setting. There's nothing, there's no information that introduces any sort of relationships among pairs of sites, or there are no covariates associated with individual sites. So you're more or less forced as a statistician to treat the sites as exchangeable. And here I will treat them as independent and identically distributed. So the things that I'm going to focus on here are mainly what does sparsity mean? You know, everybody talks about sparsity, and there are multiple examples of sparsity. Here's a list of various sorts of sparse distributions that people use in this setting. And so there's no difficulty in some sense in understanding what sparsity means. You just go and look at one of them. But what I want to do is analyze them, take them apart, and find out, try to figure out what it is, what is the common theme that all of these, and those of you who are paying attention might notice that I've said eight examples of statistical sparsity, but there are actually nine there. It's not that I can't count. So what I want to know, what I want to get at here is what is the common theme and which is the odd one out. Well, there are several common themes among these sparse. Well, they're usually referred to as sparse distributions in the literature, but in fact, they're not sparse distributions. They're sequences of distributions that have a sparse limit. And the wording is quite important here. Not everybody makes as much of a distinction here as I do, but a sequence of distributions to me is not a distribution, and the distinction is quite important. And so it's not the distributions that have the property of sparsity, it's the sequence that has the property of sparsity. And of course, all of these sequences have this limit property here, that the limit of these, I will just generically denote any of these distributions by p subscript nu, and nu is the parameter, and it's going to 0. And all of them have the property that these distributions tend to weakly to the atom at 0. And you can read them there. They're just, first few of them here are mixtures, a certain mixture of the atom at 0 and something else times some slab. So these are called atom and slab. The next 2 or 3 are, I will call spike and slab. I make a distinction between atom and slab and spike and slab because the spike will typically have no atoms. And then there are other ones that are not mixtures. So in the frequency theory literature, nearly everybody uses this one. In some parts of the, I suppose, the Bayesian literature, they tend to use these sorts of things, and also these ones. And my co-author, Nick Polson, is fond of this one called the horseshoe. Okay, and I've thrown in a few others there for just for variety. So all of them have this property, but this alone is not enough. Is not the crucial ingredient in sparsity. So let me try to explain what it is that is the crucial ingredient in all of these models of sparsity. So the interesting thing is not that these distributions tend to the atom at 0. It's how they tend to the atom at 0. So they tend to 0 at a certain rate. So this is a definition, and I will say that these all distributions are going to be symmetric, and I will say it has a sparse limit. The sequence has a sparse limit if there exists a rate parameter, which will be positive, of course. And then there is an exceedance measure. I'll say a little bit more about this, but this exceedance measure is a crucial thing. And basically it says if you look at what is the probability of exceeding some threshold, and then normalize that according to the rate, divide by the rate, and then take the limit. That limit exists, and it's the value. The value on this event is the exceedance measure evaluated on that event. And the crucial condition here is that this exceedance measure has to be a Levy measure. And a Levy measure, for those of you who have forgotten what it was, is just a measure that has a finite right-hand tail. So these are all going to be symmetric Levy measures. But they can be infinite at the origin. They don't have to be locally finite at the origin, but basically x squared has to be integrable near the origin. So functions of this type that are quadratic at the origin and are bounded elsewhere will have a finite integral. And I'm going to normalize these Levy measures so in such a way that this particular integral is equal to 1. And that turns out to be exactly the right, and it turns out to be moderately important, and it turns out it's not important for the definition, but it's important for some of the development that comes later, that this particular integral is 1. You can always normalize a Levy measure in that way. Okay, so that's the definition. What are the implications of that? It doesn't seem like I've said very much. I've just extracted from these examples what seems to me to be the common theme, and I will try to persuade you that this is indeed the common theme, and that the measure that comes out here does have to be a Levy measure. You can certainly construct sequences of distributions for which this thing has a limit, and the h is not a Levy measure. But the theory that I will I will show you in a moment does not apply in those settings. So h has to be a Levy measure. So what are the common themes here? Well, the main one, well, there are several of them, that of the distributions that I showed you, the 8 distributions that I showed you, 8 sequences that I showed you, they fall into several classes, and there are several of them that are essentially equivalent, and that basically means that they're indistinguishable in practice. There's no hope of distinguishing one from another, or from several sets of them. So they fall into equivalence classes. So if two of these sequences have the same exceedance measure, they will be regarded as equivalent. This also tells you about what you can identify and what you cannot identify. So it turns out that the rate parameter is something that you can identify. The atom at 0 is something that you cannot identify. Identify in the usual sense. You can't identify it. Sorry, when I said in the usual sense, I mean actually not in the usual sense. I mean you can identify it or not identify it to first order in sparsity. Okay. And so much of this literature was 10 years ago or thereabouts, and it was sometimes put into the big data setting, but n equal to 1 is perfectly adequate for nearly everything that I will do here, because everything is IID, and there's no big data, no big samples necessary. So this is just essentially the same as the past slide, except that I've done things a little bit fancier. But this is the form of the definition that I really want. And it's in the form of a weak convergence of integrals. So the real definition, it has to do with integrals. So the real definition is that I can replace an integral of a function w against p nu by the rate times the integral against h. So that's really what this definition. And this is for all functions w in a particular space of Levy integrable functions. So functions of this type that are bounded and quadratic at the origin, or at least quadratic at the origin, any integral of this type that I get, I can replace it with rho times an integral against h. That's basically all it is. Okay, so that's the modified definition, or it's essentially the same as I had written in the previous transparency. So I'm still going to take h in the unit form, normalized form. There's something magical, this magical transformation that occurs in all of this, which I call the Zeta transform. Got nothing to do with the Riemann Zeta function. It just happens to be the letter that I used for this. But this is an integral transformation of the Lévy measure. And it turns out that this function is, just once you defined it, it seems to occur everywhere in all of the subsequent theory. Think of it as a Laplace transform. Okay, so let's just go back to the examples that I had shown earlier, the 9 of them now. And I will just say in terms of these are the P nu families, and the exceedance measure is proportional to the slab. Exceedance measure. For the first 3 here have all got the same exceedance measure. So the first part, the first consequence of the definition is that it tells you immediately that you cannot possibly distinguish among these from data, at least to first order in sparsity. You can actually distinguish them if you take the expansion to second order in sparsity, which I'm not going to do today. You can distinguish them at second order, but not at first order. The third one, which looks pretty much the same as the first 3, except that this is the Cauchy distribution. This is Laplace, this is Gaussian, and this is the atom. But this is the Cauchy. And this third one looks much the same as the 2 before it, but it is different because the tails, the tails of this are the tails of these 2 are exponential, and the tails of Cauchy are inverse polynomial. So there is a crucial difference there, and that's the exceedance measure for this second one. This is the double gamma, and the exceedance measure, h is proportional to x inverse e to the minus x, which is the Lévy measure for the gamma process. And you see that the Lévy measure in this case is not finite because this is not integrable at the origin, whereas the Lévy measure in all, well, the Lévy measure here is not finite either, but the Lévy measure for the first 3 is finite, not finite, not finite, not finite, not finite. So these 6 and 7 here have the same Lévy measure also. So these 2, the Cauchy and the horseshoe. So the sparse Cauchy just means generate a Cauchy distribution with sigma with the scale parameter tending to 0. And the horseshoe is basically, well, this is the density function for the horseshoe, and this is the Lévy measure associated with it. These 2 are the factor. Constant factor here doesn't have any bearing on anything, so the h's are the same. And this one, I just threw this one in for no good reason, but it also has a non-finite Lévy measure. The 9th one here is the odd one out. It also tends to the atom at 0, but what happens because I have the variance of the slab, if you like, getting bigger, there's no mass escapes to infinity, but there's a derivative of mass that escapes to infinity, essentially. And so this is not a Lévy measure. So this was not sparse. So the first 3 are first order equivalent, and these 2 are first order equivalent, and the others are all non-equivalent. Okay, so just I'm going to go through a list of places where this remarkable zeta function, this zeta transform occurs. First of all, it occurs in the marginal distribution of the convolution, marginal distribution of the observables. So remember that the observation is a Gaussian convolution with the sparse family. And the marginal distribution, I will derive this in a moment, to first order. Now, there should be a plus little o of rho at the end of this. And in fact, all of these equations subsequently, there's a term that's missing, but I don't really, but it's not always exactly the same, but it's smaller than what's written. And the main thing here is that the marginal distribution is always a mixture. And the marginal distribution is a mixture which has 1 minus the rate times the Gaussian plus rho times this product, Gaussian times the zeta function. And one of the things that's remarkable about this zeta transform is that this product, phi times rho, is exactly a probability density, always. So the zeta function automatically arises there. And so there's a zeta function and the zeta measure. So this is the zeta measure. And the total mass is the zeta function. So if I divide one by the other, I get a probability density, probability distribution. But the zeta function is what occurs here. So it's the zeta measure is what occurs over here. So when I talk about the conditional distribution of the signal given the observation, it's a mixture which has a down-weighted signal distribution plus the rate parameter times this zeta measure, all normalized. And then there's something called the Eddington formula, which is goes by various names, also called Eddington-Dyson formula or Tweedy formula in the statistics literature, but it actually dates back to a paper by Frank Dyson in 1926, who attributed it to a conversation with Eddington, and it basically gives the conditional expected value of the signal. Now, I should say that this is the sparse version of it. There is an exact version of it, which is slightly different from this, but the sparse version of it just involves the zeta function, the derivative of the zeta function up top, and you see this combination occurring everywhere, basically. 1 minus rho plus rho times the zeta function. It occurs everywhere. So that's the Eddington formula. It's a Bayes estimate of the signal, if you like. Then there's this curious formula which says, asks what is the probability that the signal exceeds some threshold, conditional on the data. That's in the same spirit as this, but it's asking a slightly different question. And this is the answer over here. And the remarkable thing about the answer is that it doesn't depend on the threshold. There's an asymptotic expression, and it's a bit hard to believe or to understand how a probability of exceeding a threshold could be independent of the threshold, but I will try to explain that in a moment. Obviously, this threshold can't be 0, so it has to be a strictly positive threshold. And for the threshold, you should think of a number between, let's say 1/4 and 1 for practical purposes. But in the mathematical limit, the actual threshold doesn't matter. And then there is a Bayes factor. And the remarkable thing is the zeta function occurs in every one of these. And everything in all of these expressions depend only on the zeta function, which in turn only depends on the Levy measure. So all of this is saying only the Levy measure matters. So if you're modeling sparsity, you should forget about these sequences of these distributions and just specify it in terms of the Levy measure. Okay. So just go back to the Cauchy model. So when I talk about the sparse Cauchy, I just mean take a Cauchy distribution and scale it down. So no mixture, no overt mixture. Of course, every distribution is a mixture in a trivial sense, but this is no explicit mixture here, and the scale parameter is just equal to that rate not the rate parameter, it's the scale parameter. Okay, and if you just ask, what is the probability that the signal, Cauchy signal, lies in some differential element, small element dx, and divide through by sigma, you get dx over that, and let sigma go to 0, you get dx over pi x squared. So this is proportional to the exceedance measure, it's inverse square, and it's clearly not finite at the origin, but has a finite tail. Okay. The horseshoe the horseshoe distribution has the same sort of form, and if you take the corresponding limit, it's also a scale family. And if you take the limit as the scale parameter goes to 0 and rescale it by the inverse scale parameter, you get the same limit, apart from a factor of 2. And the factor of 2 is of no consequence. So both of these are equivalent. And the h measure, the inverse square measure, if you want that integral to be equal to 1, as I will, you have to divide by root 2 pi to make the integral, to make it in the unit form that I need. So in the Cauchy case, the rate parameter, nu and sigma are the same thing here. The rate parameter is equal to sigma root 2 over pi. So that's roughly 0.8 sigma. And the horseshoe, there's an extra factor of 2, I think, in that. Okay, so here's just to see how the argument goes. We're trying to calculate the marginal distribution of the observation, which is a Gaussian convolution with the signal. So how do I do that? Well, I take the phi out, and then I get e to the yx minus half x squared, which is what's left in here, integrated against p nu. Now, I can't take this, so the definition of sparsity involved integrals. For a certain class of integrals, you can replace the integral against, of a function against p nu with the rate function times the same integral, same integrand against the exceedance measure. But this function, it doesn't behave like order x squared at the origin, so I have to play around with it to make it be of order x squared at the origin. And there's two things I can do. To do that, I can subtract 1 out, subtract a constant, and I can also symmetrize it. Those just playing around with the symmetrization, the e to the yx becomes cosh x, and I subtract out 1, and so that line is just equal to that line just by subtracting, adding and subtracting 1 and symmetrization. That's exact. There's no approximation there. And now I replace this integral against p nu by rho times the same integral against h, rho times the same integral against h. Now there should be a plus little o of rho at the end of that. And now this integral is equal to 1. So I get 1 minus rho. By definition, h is this integral is 1. And then this is the zeta function, zeta of y. So that's how I get this expression for the marginal distribution. So this is a mixture, 1 minus the rate function times the Gaussian plus the rate function times this product. And as I said before, this product is exactly a probability density function. And it's bimodal. So zeta at 0 is 0, so this density at 0 is 0. It's symmetric, and you might be interested to see what these look like. And I've just shown what they look like for these Levy measures, dx over x to the power alpha plus 1. These are the alpha stable class. And this is what they look like, and they're remarkably similar. Well, apart from the height, but the positions of these maxima are all around about 1.6 to 1.8 for the whole range. And for a very wide class of families, this is what they look like. And here's another pair, one of them. So this is the inverse square, is that one. And then the corresponding one for a Gaussian. And even for the Gaussian, you see the maximum still occurs around 1.6 or so. But there's big difference in the tails, and that's where all the action is taking place. Okay. So for statistical purposes, at least there are a couple of parameters that you tend to estimate. You'd always have to estimate the rate parameter, and that's just estimating a parameter in a mixture distribution. This is a mixture, so this is exactly a probability distribution, so there's an associated likelihood, and the rate, if a root exists, it will be unique, satisfies that condition. Okay, I will not say anything more. So I'll say a few words now about the connection with false discovery rate and Benjamini-Hochberg. So I'm going to do this proof, quote, proof by simulation. There is a theory behind it now, but I thought I would just simulate it and let you see, just let the dice fall where they might. So I've generated the signals according to the Cauchy distribution with a small sigma. Sigma equal to 0.5 corresponds to a rate parameter of about 0.4. There was a root 2 over pi factor. So I fitted the model. This has this Levy measure, and that gives me a zeta function. And the zeta function is very easy to calculate. In this particular case, there's there's a series expansion which has an infinite rate of convergence, and so there's no difficulty computing it. For the particular data that I simulated, a big sample here, the rate parameter came out to be 0.35, 3.5%, a bit less than the theoretical value. So what is the implications of that? Here, one of these sites, there are 10 to the 4 of them. Let's take site 100. Let's suppose that yi is 3.5. The question then becomes, at least in part, what is the probability that there is an appreciable signal at that point? Well, in terms of p-values, the p-value here is about 1 in 1,000 or less. So the p-value is quite small. The zeta function is 55. So that means that the odds of the signal exceeding epsilon, think of epsilon as about a half or 1 even, it doesn't matter much, is about 2 to 1. So that means the probability of activity in this sense is about 2/3. The probability of no activity is about 1/3. So an observation of 3.5, which is quite extreme, there's still quite an appreciable probability that there is no real signal. Now, there's an unfortunate linguistic terminology associated with false discovery rate. False discovery rate is usually written in the frequency theory literature as the probability that the signal is exactly 0 given the data. Well, the probability of the signal being exactly 0 in this setting is exactly 0. So all the signals are not 0. So in that sense, the false discovery rate taken mathematically literally is exactly 0. But this probability is not 0. So the various sorts of questions that you can ask, is this inverse square model a reasonable fit? Well, of course it is, because I generated the data that way. And then what is a reasonable threshold? And here, choice of threshold doesn't matter so much as long as it's not too big and as long as it's not too close to 0. Okay, connection with Benjamini, Hochberg, and false discovery rate. Well, I'll just give you a sense of what this is about. The Benjamini-Hochberg procedure has to do with tail subsets, the sets of indices for which the observations exceed some data threshold. So think of this number as being about 3 or 4. If all of the signals are 0, then you would expect this many exceedances to occur. That's just the Gaussian tail frequency multiplied by n. But given that this set contains a good deal more observations than that, a good deal more indices than that. Roughly speaking, this many of them are going to be false, and then whatever number, the rest of them are going to be not false signals. So the Gaussian fraction is roughly this. And that's sometimes called the false discovery rate, but bear in mind, it's not really false discovery in the literal sense. I'm going to use the term not quite null signals. So the set of not quite null signals are those that fail to exceed this threshold, which you don't really have to set, but you can imagine it. And according to the argument that I've just given you, the probability of this event, the probability that index I is in this set, conditional on y, is given by this, just depends on yi, it depends on the zeta function. And therefore, the expected number of not quite null signals in any set, in any subset, is just the sum of these probabilities, and in particular, the expected number of not quite null signals in the tail set is just the sum of the tail set, sum over the tail subset of these probabilities. And the question then, basically this would match up with Benjamini-Hochberg if these two expressions were about the same. And that's, I put a question mark there because I haven't proved that, but from the simulations, I calculated the sum of this term, and that's this column. So this is in the. I picked a threshold from 3 to 5 here, and calculated how many of how big the tail subset was, how many observation values were bigger than that, and this is how many were generated. This is the Gaussian probability. I'm nearly finished. And this is the sum. This is the sum. Yeah, the sum of these probabilities calculated, conditional on y, calculated, and you can see that they more or less match up. They're roughly equal. Okay, and you can actually prove, in some sense, that these are theoretically the same. I'm going to more or less time. So and let's see. I better move on. Just going to say a little bit about the nature of the conditional distribution of the signal given the data. In the Cauchy case, this is what the posterior distributions look like. They're bimodal, basically. And if you look at if you want, how to say it, if you pick a fixed y value and ask what is the probability distribution of the signal given that y value and that let rho go to 0, you'll get a trivial answer. It's always 0. But if you want a non-trivial answer, you have to let the y go to infinity and the rho go to 0 and keep this product fixed. And if you do that, the posterior distributions look like this for increasing, for decreasing or more sparse. This is the most sparse, so the sparsity rate here is 0.1%, and up here it's 5%. And what happens is, and the way that this is done here, there's the atom, or it's not an atom now, but the spike at 0 contains roughly 50%, and the rest of it contains 50%. And no matter where you set the threshold here, there's going to be eventually 50% to the right and 50% to the left, as long as the threshold is not too close to 0, and as long as it's not too close to the observation. And this is the exact calculation for the Cauchy. The exact calculation for the horseshoe is there, and if I flip back and forward, you can see that they're not the same, but you have to look very carefully. And that was part of what I said, that these were indistinguishable. And, and I think I will move on and just go to the, thank you.
You mentioned that basically the same kind of analysis when there are regression structures gets a bit more complicated. So can you elaborate a bit on that and what are the reasons?
Well, the reasons are that in the regression case, you have information about inner products between the various covariate vectors, and there's nothing of that sort in the structure, in the setup that I described. So there are, so there is that aspect, so that's some structure there. Also the regression coefficients, least squares regression coefficients are not independent, and if you take the sufficient statistics, X transpose Y, those are not independent. So there's lots of things that are different, so it's not clear that in the regression case whether you want independence of the coefficients or not, and certainly the data that is associated with each component is not independent.
Very interesting. Peter, I just wanted to ask you, how do you see this, these latest discoveries, how do you see them impacting on what is done at present, impacting on practice?
Yes, how do I see it impacting on practice? Well, I suppose it's closest to the areas where it would be most practical would be the areas where Benjamini-Hochberg procedures are used. And basically the difference between this and Benjamini-Hochberg is that this gives you for every site what the probability of an active signal is at that site. And it's not averaged over any tail subset, so it gives you exactly, it gives you the more direct assessment of the likelihood of getting a signal, an appreciable signal at that site. So anywhere that the Benjamini-Hochberg procedure is applicable, this is equally applicable.
Let's thank Peter and both speakers.